Hello and welcome to this new video in which I'm going to show you how to perform the vector error correction model using Eviews. So you need to know first of all that the vector error correction model is a econometric model that is used when some requirements are satisfied. The first requirement is that all variables need to be stationary at first difference. So as you know, in standard vector autoregressive var model, we need to have all variables that are stationary. So the second requirement on vector error correction model is that all variables need to be co-integrated, meaning that there exists a long-run relationship. The co-integration can be in the Johansen co-integration when we have more than two variables to put into a relationship, or it can be a Granger co-integration when we only have two variables to explain. So we have here a data set in which we are going to apply our example. We have 5 variables. First variable is y, and we have 4 other variables that are x1, x2, x3, x4. So we need to explain the variable y using our variable x1, x2, x3, and x4. So we're going to follow all the steps that is needed in order to be able to perform and interpret coefficient of vector error correction model. So the first time you are watching one of my video, do not hesitate to subscribe and activate the notification bell in order not to lose next publication, and do let us thumbs up. It will be a pleasure to know that all effort we are making are helping you improve your level in statistical model for social sciences. So the first step is though to check for unit roof. So we're going to start by our variable y. So let us open our variable. So to check for unit roof, as you know, you just need to go in view, then unit roof test. When we are on unit roof test, we have by default the augmented decay flow test that is been highlighted. So we have many other possibility like decay Fuller, GLS, we have Philippe Perron, we have KPSS, and so on. So we'll keep the by default option of augmented decay Fuller test and then click on OK. And you can see that for our variable y, if we consider a 5% significant level, we can now accept the null hypothesis that our variable y have unit root. So mean that our variable is not stationary if we consider a 5% level of significance. So let us check for first for the first different unit roof. So then go on view unit roof and then select first difference, then OK. And we can see that variable is now stationary at first difference. So we can do the same thing for variable x1 view unit roof and first difference for the fuller test, then click on OK. And you can see that the p-value is more than 5%. Significantly high by 5%, considerably higher than 5%. Then we can check for unit roof at first difference, and we can see that the p-value is now less than 5%, meaning that our variable x1 is stationary at first difference. We can do the same thing for all other variable. And can verify that I have verified that variable x1, x2, x3, x4, and y are stationary at first different. So as we have demonstrated that our variable are stationary at first different, we'll first of all go to estimate our standard var. Even though we know that var model is not appropriate because of the fact that our variables are not stationary. So let's go on Guid and then go on estimation. No, not estimation, go on Guid estimate var. After that, let's go on endogenous variable section and then type the name of our different variable. The first variable is y, x1, x2, x3, and x4. How to choose the optimal lag to estimate our model. We'll see how to do so. For now, we will keep our 1 to 2 lag endogenous interval as it is, and then click on OK. And you can see that our var2 model has been estimated. Our standard var2 model is not appropriate because our variables are not stationary. So how to know the optimal lag to estimate in our model? So we go on view and then lag structure and then lag length criteria. We have 3 lag by default because we don't have so many observations in our var by default. We can propose more than 3, but we keep the 3 by default. Then click on OK, and we can see that in this case, one of our model, like one of our criteria, Akaike information criteria, AIC, show that we can estimate a var3 standard var. So other criteria have shown that you must estimate a var1 model. The limitation in the choosing for 1 lakh var model is that if you are going to estimate our vector error correction model later, we lose lag because when we have a standard var of order p model, when we want to estimate our vector error correction model, we must estimate a vector error correction model of order p minus 1. So if we choose for a var1 model, we'll estimate a var0 model, which is not optimal. So we keep our var3 as optimal lag for vector autoregressive model. So we'll delete 2 here and put 3 as optimal lag, and then click on OK, and we can see that we have our var3 model. So as we have already checked the stationarity and our variable required verify the first requirement of first order stationary, we check for cointegration. After estimating our var3 standard model, we go on view and then click on cointegration. So we have many options here. The by default option is the option with intercept and not trend. We select this option, optimal lag 1 to 3, as we have done previously, and then click on OK. And we can see that our trace statistic test, as we see on this here, that a trace test indicate tree cointegrating equation at 5% level. So we can now accept the hypothesis of cointegration among our variable. So as our variable are cointegrated, we can estimate our vector error correction model. So we go on estimate. Then as we are going to estimate our vector error correction model, because of cointegration between our variable, we'll select the option vector error correction. But here we'll choose for 3 lag because when estimating a vector error correction model, we lose lag. So we'll have a optimal 2 lag for our vector error correction model. So we click here on OK, and we can see the vector error correction model that have 2 parts. The first part is a cointegrating equation, which is a long run equation, and we have the short run equation that is the relationship that is will apply in the short run. So let us start with the long run equation. So notice that in long run equation, as is appear in Eviews, the coefficient, the first variable, the explanatory variable here is y. So we have x1, x2, and the coefficient here should be interpreted as opposite value. So we have here that it appears that the coefficient of x1 is negative, but we will interpret a x1 variable as having a significant, a positive impact in the long run on y, because this is the normalized equation, meaning that all variables are in the same member of the equation. So if we throw the explanatory variable in the second member of the equation, we'll have opposite sign but have the same value in absolute value. So we will notice that the value into the last value of that is into code here are in the t statistic. The value into bracket is standard error. So here this value will be interpreted, will be considered, the coefficient will be considered to be significant if the value, this value is in absolute value more than 194, which is the 96, which is the critical value for a student statistic. So here the variable x1 is significant and have a positive impact on the variable y. The variable x2 have a t statistic that is more than 185 in absolute value, meaning that the variable x2 is significant and the sign is positive. Is negative because as for the reason that we said earlier, that all the normalized equation, all variables are in the same member, and when we throw the explanatory variable in the second member of the equation, we have negative opposite sign. So x3 have a negative impact on the explanatory variable y, but the sign is positive. The variable x4 is not significant at 5% level in the long run because the student statistics is less than 196 at 5% level. So here is a long run equation. In the short run equation are here. So we can notice first of all that our error correction term is negative and significant because student statistics is more than 195. 1.95, which is the 5% threshold of student statistics. So the coefficient of cointegration term is negative, which is the good sign, meaning that there exists a cointegration equation that confirms the existence of a cointegration equation and the correction mechanism when there is a shock on one of the variables. So in the long run, we can notice that variable lack two value of the y of the explanatory of variable y have a significant impact. But this time, the coefficient of the short run equation are not interpreted as opposite as we did it in the long run equation. In the short run equation, the coefficient, the effect, the sign of the effect is the same as we see on the result of estimation. So lack one value of variable y have no significant effect because of the fact that the student statistic is less than 1.96, but lack two value of y variable have significant effect. So we can notice that variable x1 have no significant effect because of student statistic less than 1.96. Same for the variable x2, lag 1 and lag 2. Variable x3, lag 1 is not significant, but the effect of the lag 2 of variable x3 is significant and negative. So x2, x3 have a significant negative impact on variable y. The variable x4 is not significant, have not significant impact on variable y. Only variable x3 have a significant impact at in the short run through it lag 2 variable. So in the long run, we have x1, x2, and x3 that have significant impact on the variable y. only the variable x4 have no effect at in the long run. In the long run, x1 have positive impact in the long run. X2 have negative impact on in the long run. X3 have significant and positive impact in the long run, but X4 have no significant impact in the long run. But in the long run, in the short run relationship, only three variable X3 significant and have negative impact. Two is lack to variable. So that's what we can say for the vector error correction estimation. You can go to check for some hypotheses on the residual, like normality, homoscedasticity, as well as autocorrelation. So we go on view, then residual diagnostics. We can test for normality here with Koleski of covariance. Then click on OK, and we can see that the joint variable show that the variable are the p-value of joint normality is less than 5%, meaning that we reject the null hypothesis of normality of residual. But some of component of our variable, the first, the second, and the third component are normally distributed because p-value are more than 5%. The fourth and fifth component are not significant because it's the vector of 5 variable. All components need to be normally distributed, but the join is not significant. But when we look at kurtosis, the kurtosis is jointly normally distributed, but the problem is among Jack-Bera component. So the variable is not statistically significant. The normality is not satisfied. So we can also check heteroscedasticity in residual test, and then heteroscedasticity. The second option is the good with cross term. Not available, we'll go on residual diagnostic, and then first option white, heteroscedasticity, no cross term. And we can see that the results show that the p-value of our heteroscedasticity is more than 5%, meaning that the null hypothesis of this test is the constant of the variance, which is the homoscedasticity. The p-value here is more than 5%, meaning that we accept the null hypothesis of constant variance, meaning that our error term are homoscedastic, which is the good hypothesis. The last hypothesis to verify is to the autocorrelation in residual test. We use, for example, the Portmanteau autocorrelation test. Then click on default value of 3 lab. Okay. And you can see that the p-value is the joint p-value, which is the one that appeared. The third p-value is 0.38, which is more than 5%, meaning that we accept the null hypothesis of non-autocorrelation, meaning that we are happy about our model concerning the autocorrelation and homoscedasticity. The only hypothesis that have not been verified for this model is the normality, which can be neglected in many of the cases. So that's it for this video on the modeling of an interpretation of a model using vector error correction model. If you have not done so, do subscribe and activate the notification bell in order not to lose the next video. And let us thumbs up to know that all the efforts we are making are helping you improve your skills. So anytime soon.